So what am I going to tell you about? So, well, we're all interested in various aspects of amplitudes and geometry, things related to amplitudes. In particular, this workshop, I guess, has Amplituhedron in the title, and I have to be honest that I'm not going to tell you immediately I'm going to tell you some things that are related to the Amplituhedron, I guess, but are not directly involving the Amplituhedron. However, what I want to get to by the end of the talk is a description in perhaps a language that you haven't seen before of the BCFW recursion relation. And the BCFW recursion relation is something that, in the context of n equals 4 amplitudes, is a way of thinking about triangulating the Amplituhedron, some geometry, and chopping it up into pieces, and then you can compute the canonical form for each piece and extract the amplitude from that calculation. So what I want to show you is a generalization of kind of what I think is a natural generalization to a natural other class of objects that goes beyond scattering amplitudes, which also has a BCFW recursion relation of a generalized kind with new interesting types of terms in it, and perhaps therefore suggests an interesting generalization of the Amplituhedron. But that's not something that has been worked out. What I am going to show you is the generalized recursion relation. Okay, and it involves pictures like this. I'll explain what they mean. And the objects are correlation functions of light-like Wilson loops. Okay, and a single light-like Wilson loop is dual to a scattering amplitude in the context of planar n equals 4 super-Yang-Mills. Okay, so how does that work? So if you're interested in a scattering amplitude, you have a process with a bunch of light-like momenta, P1, P2, up to Pn. And they obey momentum conservation, and they obey this light-like null condition. So these are the two constraints these variables obey. And you can translate that, you can solve this momentum conservation by telescoping, and rewrite the momenta as a difference of some dual coordinates. This implies that you've got some natural ordering amongst the legs, cyclic ordering as you go around, in order to make this change of coordinates natural. That is the case if you have scattering and amplitude carrying color labels such as gluons in a gauge theory. Okay? And in particular, if you take the planar limit, then you can restrict yourself to color structures that only observe this single cyclic ordering amongst the external data. Okay, so kinematically, simply by this change of coordinates, I can rewrite this thing as a polygonal contour. I take each edge, I put the edges end to end, and I close my contour due to this momentum conservation. And each edge is null because each of the momenta was null. So you get this light-like, piecewise light-like contour as you go around. Okay, so then the duality says the amplitude with these kinematics is equal in some slightly more precise sense than twiddly line to a Wilson loop computed on this light-like contour in the gauge theory, n equals 4 super-Yang-Mills. Okay, and a Wilson loop is the trace of the path-ordered exponential around your curve of the gauge connection, A. All right, and okay, so this duality, as presented, comes about like this. It was originally proposed by looking at strong coupling, in which case it was suggested that you should think of gluon amplitudes at strong coupling in n equals 4 as being described by open strings scattering inside ADS. And then by a T-duality transformation on the world sheet of those open strings, you can rewrite this as a minimal surface that extends in ADS, whose boundary is this piecewise light-like contour. So this was work by Aldine Mulder-Sanger, which was sort of near the start of all of this.
Sorry, just very basic question. So the picture you have with the x-size, that to me looks like that's a one-dimensional picture, but the surface suggests two-dimensional.
Okay, so great, good. So what are the dimensions? Okay, this is a cartoon. The momenta live in 4 dimensions, right? So 4 space-time dimensions. They have 4 components. Therefore, these dual x's live in some 4-dimensional space with Minkowski metric, so that I can have these light-like edges. Now the contour itself, you're right, is 1-dimensional. And then in the context of ADS CFT, which is what I really meant down here, I take that 4-dimensional space and I extend it by a 5th radial dimension. It's the radius of ADS. So I've got a boundary, which is Minkowski space, and a radial dimension. And then this scattering, open string scattering, actually takes place at some point in the bulk of this ADS. This minimal surface is a surface that extends in the bulk and then ends on this contour on the boundary. So it is indeed a 2-dimensional surface with a 1-dimensional boundary inside a 5-dimensional ADS with a 4-dimensional boundary.
Sorry, once more for the picture. So it has like a radial dimension or something. So this is like, visually, would this be like taking a cone over this 1-dimensional thing?
Not a cone, because so that space has a hyperbolic metric in it. So, you should really think of, I don't know, I should draw a cartoon, better cartoon. Where's the chalk? Okay, so here's the boundary, which is really 4-dimensional. Here's the polygonal contour, which is 1-dimensional inside the boundary. And here's the radial direction of ADS. There's some hyperbolic metric in this, so distances go to infinity, actually, as you approach the boundary. And then there's some minimal surface that sort of extends down in some way, which is 2-dimensional, and it extends into this radial dimension of ADS. That's maybe a slightly better cartoon. All right. This I was not going to write up by hand, obviously, but this is just a list of lots and lots of references, and many, many people have studied lots and lots of different aspects of this duality. And I mentioned Aldine Malvasein already. Studied these sort of aspects of this T-duality transformation between the open string scattering and the minimal surface picture. It has consequences related to symmetries of scattering amplitudes, because there's an additional conformal symmetry that arises called dual conformal symmetry, which has a supersymmetric extension. You can start doing computations and check on both sides in weak coupling that the amplitude and the Wilson loop calculations actually agree, and you get the same answers out of the relevant pieces. You can study these minimal surfaces at strong coupling in much more detail, and there's a nice classical integrable system picture that allows you to try to understand these minimal surfaces. There's tremendous progress in understanding both objects, or the Wilson loop really, at finite coupling by means of studying various limits and what's called an operator product expansion, pentagon operator product expansion by these authors, which allows you to, if you understand the components of that expansion, it allows you to give a sort of a small distance expansion around certain limits of this Wilson loop where it attains some kind of singular configurations, where many lines sort of want to become collinear to each other, parallel to each other. Obviously, it has lots of connections to positive geometry and spaces like the Amplituhedron. It has lots of sort of extra symmetry arguments that you can apply to this based on the fact that you can formulate things in terms of Wilson loops. So some of the supersymmetry is not manifest, so-called Q bar. So some of the supersymmetry requires careful investigation, but then you get some powerful integral differential equation which arises through that investigation and gives you lots of strong constraints on these objects that you can use to compute. Okay, so what the main point of all of this was that there are lots of aspects to this. Some of them are sort of naturally amplitude-y type aspects. So things like, at least the BCFW recursion relation originally arises in the context of thinking about scattering amplitudes. Things like I guess the minimal surface picture and also the OPE are very naturally on the Wilson loop side of this correspondence. Geometry, the Amplituhedron, well, this maybe is a question more for the audience, but intrinsically the way it's formulated in terms of momentum twisters, it actually feels more naturally closely related to the Wilson loop side of the story rather than the amplitude side of the story. Now, since the two objects agree, then I guess it becomes slightly moot, but okay, so, well, that's just a point for discussion, perhaps. I mean, there are other generalizations. There's other ways of thinking about the amplituhedron. There's a momentum amplituhedron, for example, which is perhaps more naturally related to the momentum space in the original scattering amplitude picture. Okay. So we have BCFW on the amplitude side. So the point of that is something that does exist on one side normally has a natural counterpart on the other side, and it looks completely different, but it gives you the same description of ways to compute the object. So like the perturbative computation of amplitudes and the perturbative computation of Wilson loops look completely different. They give you the same answer. BCFW is the thing that I'm getting towards, which has an actual amplitudes picture. You deform some momenta with a complex parameter, you study the amplitude as a function of this new complex parameter, and you study its poles. And then you understand something about its residues on those poles, and that allows you to reconstruct the answer. So that's an amplitude story, but actually it also has a natural Wilson loop counterpart, and that goes under the name of holomorphic linking. And this is part of a general story of formulating supersymmetrically this Wilson loop picture in terms of momentum twisters. But in particular, this holomorphic linking story is due to Bullimore and Skinner. And it's a reconstruction of the same BCFW recursion relation that you already knew was there from the amplitude side of the story. Okay, but we're going to revisit that point. Okay. So, first, the context, though, of what I want to do. So here what I want to study, instead of a Wilson loop, is a correlator of multiple Wilson loops. And in so doing, I'm no longer dual to an amplitude, at least not directly. Okay, so it's just another object that naturally generalizes a single Wilson loop. It's got similar data to it, but more copies of it. So I'm going to imagine, for example, two light-like squares, and then I'm going to try and compute the correlation function of these two operators with each other. So it's going to be something that depends on the data for both loops. Okay. One reason for wanting to think about this is that, so this minimal surface picture would change, and its strong coupling, what you would expect is to see, in the large n limit, you would expect to see a minimal surface again, but whose boundary ends on both of these contours, and it has a cylinder-type topology that stretches between the two, okay, rather than a disk-type topology. So I'm changing the genus of the underlying world sheet. So we've described the string, classical string, or minimal surface that would end on these contours. why would you be interested in that? Well, it's perhaps a slightly baroque way of approaching the spectrum of the theory again. If I exchange a minimal surface that goes from one to the other, in principle I'm exchanging all closed string excitations between my two objects. And closed string excitations means gauge invariant local operators in the gauge theory. So this object should contain information about the spectrum of the theory. Right? The scaling dimensions of the local operators in this conformal field theory. And that, in the planar limit, is known to have an integrable structure to it. So there's lots of structure related to these scaling dimensions. Perhaps that will exhibit itself if you study such an object. Okay, so that's maybe a vague motivation for the future. Here what I'm going to ask really is, can we compute these things? Can we extend the techniques that we've used in order to compute a single Wilson loop to compute these correlators of multiple loops? In particular, I'm interested in their supersymmetrization, which is going to lead me to this Mason-Skinner formulation for twistorial super-Wilson loops. And then the thing that we're interested in here will be this BCFW recursion and the holomorphic linking. And there's also a story about the Q-bar equation, which I'm probably not going to cover today. Can describe in more detail if people are interested. Okay. All right, so some basic, the basic setup of what happens when you compute Wilson loops. So we've got our light contour, C, and we want to compute the expectation value of this operator. And what do? Well, you start by simply expanding it in perturbation theory. So I've got an exponential. I start expanding it, so my object will start with 1. And then I'll get the first interesting term where I have 2 insertions of my gauge field. I mean, there's a term where I have a single insertion of the gauge field, but that can't, the expectation value of that will vanish. So the first interesting term will be the quadratic term. I'll have 2 insertions of the gauge field from expanding this exponential. I have to integrate them around my loop. So they're sit at positions parameterized by T1 and T2. And I have to integrate this around my loop with these insertions. And then what does it mean to compute the expectation value? Well, I have a propagator that takes me from a gauge field at one of these points to the other, which is just this object here, which I've written out actually in dimensional regularization. So it's just the square of the distance between the 2 points, squared, modified slightly for dimensional regularization. There's some color structure, some color labels that I pick up because these things sit in some representation of the gauge group. I'll take the fundamental representation of SUN here. My gauge group will be SUN. And there's some Lorentz structure, which is all diagonal. And so one thing you will notice is that the color structure will go away. I'll contract these color labels here and here, and I'll pick up some overall color factor, which is just a function of n, which is a UN or SUN, depending on what I chose for my gauge group. And then I've got to take this function of x and integrate it in all positions around this loop. And you get 3 classes of diagram. One which simply vanishes, because this dot product here will vanish for a light-like edge. So because the edge is light-like, this one will vanish. You get some divergent ones where the dim reg epsilon is important, and you get poles in epsilon, actually a double pole from here. And then you get some diagrams which are finite and can be evaluated at epsilon equals 0. Okay. All right, so there's a divergent diagram. Very simple. It's very simple kinematic dependence. It's a double pole in epsilon. Here's the finite diagram evaluated at epsilon equals 0, and I've just chosen one representation for it. You can do these double integrals that have to be done, and surprise, surprise, you get a bunch of dialogues out, which is a double integral. So we've just rewritten one double integral as a bunch of other double integrals in some explicit form for these dialogues. Okay, so some observations that come about here. One is that if I add up all these finite diagrams, I get something that is actually not conformally invariant. And the reason for that is that I had these divergent diagrams, and there's an anomaly in the conformal transformation, conformal ward identity, due to the fact that something funny is happening at these corners, and I get something that's divergent. And the end result is that this is the equation that's actually obeyed. It's not zero on the right-hand side, so this is a special conformal transformation on this function. Gives me something which is localized over each corner, so it's something, sum over I, some stuff that's happening at each corner times the log of the only non-zero distance near that corner. Okay, so this is anomalous there. But that's as good as having conformal symmetry. Once you know the anomaly, you know the implications of conformal symmetry. Okay. All right. So now so what I showed you was the first order computation. If you try and compute to all orders, the general structure that you find is that you get a factorizing set of divergences localized at each corner, the first term of which I showed you with that double pole in epsilon. You get a factor that accounts for this anomalous conformal transformation, which is really the exponential of that same function I just showed you, with the function of the coupling. As I expand in higher and higher orders in the gauge field, I'll get a series in the coupling G, the first term of which was that number that we had in the previous slide. So if I take the first term in this, is 1, and then the next term will be what I just showed you, and then there's all higher order terms from expanding out this exponential and expanding out the light plus anomalous dimension, which it sits here. It's a function of G. That's the anomalous conformal part. And then there's whatever's left over that's just literally conformally invariant. Some remainder piece, remainder factor, finite, conformally invariant, which just sits here as Rn. Okay, and you only start getting Rn when you have enough kinematics to be able to make invariants under conformal transformations, which in this case means you need at least 6 points on your Wilson loop in order to have a conformally invariant cross ratio. Okay, so that's the general structure. Okay, now we want to replace that structure with a correlator of multiple loop operators. And the claim is that the general structure will be very similar. You will have, for the same reasons, you will have divergences, and for the same reasons they will be localized at the corners of each of the loops that we're interested in computing the correlation function of. So for each loop, for 1 to m, loop. So loop okay, so right. So there's this slightly awkward terminology where we talk about a loop expansion, which is the series in G Yang-Mills. Okay, and I just mentioned here I've got higher and higher loop corrections inside this function gamma cusp of function of the Yang-Mills coupling. And I've also got multiple loops. So we need a new name for this number m, which is not the number of loops. We can call it the number of operators. Rather daftly internally, we've been calling it the number of Wilsons, because there's multiple Wilson loops in here. Obviously, you can't have more than one Wilson. So, I don't know, we'll have a number of polygons, or number of contours, or I'll try and, if I say loops and it's not clear, I'll try and distinguish the two. But anyway, there's a number of operators that we've got here. And there will be an anomalous conformal transformation again, and that will take exactly the same form that we saw. You sum over all of the corners on all of the loops with the same anomaly. So that will be taken care of by putting in exactly these same functions, factors fn, here for each loop in the product over all loops. I take out all that global factor, and I'll be left with something that's conformally invariant. And then this is some new interesting conformally invariant function that depends on n1 all the way up to nm, And when m is 1, I get back my single Wilson loop, but m could be bigger than 1, could be 2. Right? And I get an interesting new conformal invariant function to study here. Okay. Only when m is 1 is it the same as an amplitude. Okay. Right, and there's another thing to bear in mind, which is just to do with color counting and connected diagrams and so on. And that is that one piece of the contribution, if I want to start computing two contours in perturbation theory, and I start exchanging whatever propagators, there are also vertices, Yang-Mills vertices, diagrams that look like this, and look like this, and stuff that goes between, but some of the diagrams have nothing that goes between, right? So therefore, a piece of the answer will be literally the product of the two individual Wilson loops, diagrammatically, and then there'll be other stuff, so it's this plus other stuff, in which we've got at least some stuff going across. And then there can be stuff on the inside, doing whatever, but there'll be at least some stuff going across. Okay, so this piece we'll call the connected part. And that's just a definition. Okay, the connected part is the thing we computed minus the product of the two individual Wilson loops. And it just means it's all the diagrams where something is going across. Okay, and that story just factors through all this divergent story, so you can write literally the same equation for these finite parts. Okay, so if I had two loops, there will be a connected piece as well as the factored piece, and the connected piece will actually be suppressed in the large n limit. So the leading term in the large n limit will be the factored piece, and then the connected piece will be at least 1 order 1 over n squared down for large n. Okay. Similarly, if you have a correlator of 3 loops, again, there'll be a piece that comes from the purely factored piece, and then there'll be pieces that come from the connected parts of 2 loops with the factored piece of a third one in all combinations. That will be a 1 over n squared suppressed. And then there will be the new fully connected piece that involves all 3 loops, which will be 1 over n to the 4 suppressed. Okay, so let's do this simplest connected contribution of two contours. Well, it's the same computation that we just did before, except that there's one small difference, which is the color structure is different because I've got gauge traces on each loop. So now, instead of trace TATB, I've got trace TA, trace TB, and this is going to give me 0 in SUN, or, well, not 0 in UN, because then I'll get a trace contribution to my fundamental representation generators. Imagine I'm computing in U1 for the time being. Then what am I going to get? I'm going to get this thing multiplied by 1 for the color structure. And then I'm going to sum over all the finite diagrams. That was a finite diagram that we had before that goes between the ith edge and the jth on this loop, the jth edge on that loop. And that's going to give me some function, which when I add it up, all the diagrams, I'm going to get, I had all those dialogues, for example. I can add up all those dialogues for this new configuration, and I'll get something. But this time I'm going to get something that's actually conformally invariant. Okay, there's no divergent diagram that's connected. All the divergences are in this factored piece at this order. And so I get something that's conformally invariant, and here's one way of writing it in terms of dialogues and logs. Okay, where I make some cross ratio that kind of goes across, so it involves I on one loop and j on the other loop. And so you have distances that go across in all possible ways, and you take the cross ratio of those. Okay, so you get something interesting and new already at the leading order in the abelian theory. That vanishes in the SUN theory for the color reasons, but if I do go to the SUN theory, then the leading diagram that I'm going to get that doesn't vanish for color reasons just sends 2 propagators across between the 2 loops, and then you have to add up all ways they can connect, And now, because there's only 2 insertions, the order doesn't really matter on each of the loops. So actually this thing factorizes. And I'll pick up some color factor that comes from taking this combination of traces. And then the actual kinematic structure, I get a g to the 4 because I sent 2 propagators across. So I've got 2 orders up in g squared. In some sense, each dot gives you a g. Got this color factor. And then I've got the square of that function that we've just computed in the abelian theory. So I get something of weight 4 made of dilogues and logs, and it's a perfect square. And if I wanted to compute this thing for 3 loops, I would get the product over the 3 evaluations of this same function between the 3 loops. Okay. So simple computations to get some answers out, and they're all conformally invariant. Right, now we've talked about conformal symmetry. It's very natural to describe this light-like geometry in terms of momentum twistor variables. And I probably don't need to remind this audience, but these objects, we can think of these as living in complex projective 3 space, and they are made up of, well, if I take a light-like edge between 2 of my neighboring points, this can be factored in this bispinner representation into a pair of this outer product of 2 two-component spinners. If I take the chiral half, the lambda, that will be my first half of my z. And then if I compute x times lambda, which is sometimes called mu, pair that up, I'll get something that is a 4-component object. It's modulo scaling in the lambdas. Right? This is homogeneous in lambda. So I can mod out by scaling in the lambdas, which does not change my x's if I scale these lambda tildes opposites. So there's this redundancy in this picture, which is why this object lives in P3. And then the kinematics of the light-like contour in space-time just becomes a piecewise intersecting set of one-dimensional curves or lines in this projective 3 space. And then the corners will be represented, if I have a sequence of lines mutually intersecting one another, I can just record the data by locating the corners, the intersection points, as I go around the contour. And these will be Z1 up to Zn for a single loop. And if I have multiple loops, I have 2 copies of the data. So I'll have one set of Zs and another set of Zs for my other loop. Gives me the kinematics for the other loop. Okay. Right. Now, in order to study scattering amplitudes, which have more than just gluons, they have fermions and scalars, and a supersymmetry structure that relates all those components to each other. It's useful to extend this Wilson loop picture, which we saw, to include a supersymmetry. And that's actually quite a complex operation, and in some sense it's most naturally handled in this momentum twistor space story. Okay, so what I'm going to do is I'm going to follow what Mason and Skinner did in order to try and provide a supersymmetrization of the Wilson loop. And they worked in momentum twistor space. Actually, they extend it by, in order to have the supersymmetry, they extend the momentum twistor by 4 extra fermionic or Grassmann degrees of freedom, chi, and then we have a momentum supertwistor, which is the pair Z chi. It lives in this projective super space, CP3/4. Right, and then, perhaps somewhat surprisingly, although it's also related to things like the MHV expansion for scattering amplitudes, you can rewrite the n equals 4 super Yang-Mills action defined in space-time as an action defined on this momentum twistor space. And when you translate it to momentum twistor space, the way to think about this is as a holomorphic Chern-Simons theory. So it's a 3-dimensional, ignoring the fermions for now, it's a 3-dimensional space, actually complex. And on this three-dimensional space, it's natural to study a gauge theory which has a Chern-Simons structure. Okay, so that's what this term here is. The holomorphic Chern-Simons theory. This A is a 0,1 form gauge field living on this space. Okay, and I'm meant to integrate some holomorphic measure versus this 0,3 form that you get by taking this Chern-Simons combination here. All right, so this is called a holomorphic Chern-Simons theory. And actually that would give you the self-dual part of the n equals 4 theory. If you want the full n equals 4 theory, which includes not just the self-dual part, but all perturbations away from the self-dual part, in this picture you have to add a bunch of non-local interactions. And these are things that are localized on lines in this twistor space. So they correspond to things that would be local in space-time, local interactions happening at a point x. But a point x in space-time corresponds to a line in this projective space. So we have to integrate over lines, again, the supersymmetric version. And then there's an infinite sequence of interactions, which can be recombined into the kind of a log det form of the Chern-Simons covariant derivative, okay, which is covariant derivative localized to the line x that you're interested in looking at. All right, so it looks a bit funny, but this is meant to represent the n equals 4 super-Yang-Mills dynamics from this momentum twistor space perspective. Okay, and now the question is, how do we formulate our object that we're interested in computing in this formulation? So the idea is that you take some rational curve, some one-dimensional curve in this complex curve in this CP3. Given that, on that curve, you can always find the holomorphic frame, which is called H, which is such that if I take the covariant derivative, d bar plus A, with connection A, and I do H inverse H, I just get simply the anti-holomorphic derivative. Okay, so I can covariantly rotate everything to be, if I want some covariantly holomorphic thing, I can find an H for this curve C so that it can be rotated so that things just become literally holomorphic. Okay, so this you can show this holomorphic frame obeys this simple equation. It's just d bar plus A on the holomorphic frame vanishes. Just follows from the left-hand side. And then what we want to build is a parallel transport operator that takes us from one point to another. One point on our curve C to another point on our curve C. Okay, represented by some point Z prime in the original space, the CP3. So what we do is we simply take H of Z prime inverse. Because of this U obeys the same equation, but with the boundary condition that when I put Z equal to Z prime, I get the identity. So I found a solution that obeys this equation with this boundary condition by constructing this holomorphic frame. And moreover, also it's clear by the construction that if I concatenate two parallel transports on the same curve, then I'll get the sort of the obvious parallel transport on that curve between the endpoints. Okay, so in slightly formal language, I'm just telling you what a Wilson loop is again, I guess. Okay, so now what curve are we going to take? So the curve we're going to take is the one that we've drawn. So it's a curve that's going to be made up of n degree 1 components, so n lines. And each line is going to be specified by 2 points, zi minus 1 and zi, like here. And then it will be parameterized by some complex parameter. So here's our line, xi corresponds to x3, this line here. And I can choose some local complex coordinate s on it, such that s equals infinity will correspond to this point, and s equals 0 will correspond to that point. Okay. And now, the operator that we want to define is, formally we can think of it as again, a trace of a path-ordered exponential of the integral of this connection around our curve C, and it's defined simply by concatenating these parallel transport operators for each line individually from one point to the other as we go around. Okay, in principle, we should pick some base point to start, but because we have the trace, and this is cyclic invariant, and we have the concatenation property, it's clear that this is independent of our choice of base point Z. All right, and then how do we compute in this theory? Well, I showed you for the ordinary bosonic gluonic Wilson loop, you expand that path-ordered exponential and contract the gauge field insertions with propagators. Same here. I take this object U, I solve this differential equation with the appropriate boundary condition. I get this, what we could call a path-ordered exponential with an infinite sequence in integrals over this gauge connections, insertions of these gauge connections, each sort of correlated so that each one talks to its neighbour with the correct singularities. Okay. So this is all directly parallel to the standard story that I showed you before, just for gluons. But now our A is going to be on this supersymmetric space as a function of the super twister. So as well as gluons, it will contain fermions and scalar degrees of freedom in the theory as well. So this is a way to supersymmetrize. Okay, so when you start computing in this formalism, what you find is, well, you need to make some choice of gauge, and the standard choice is to make a kind of axial gauge choice, which means picking some fixed reference twister, Z star. Okay, so that's just a gauge choice. It shouldn't end up, Z star should cancel out of the end result of all your computations. But term by term, Z star will be everywhere in the way that you compute in this. In particular, it will appear in the propagator between 2 points, 2 twisters, Z and W. There'll be a propagator, which you can write as an integral over something which essentially sets these three objects to be collinear. Okay, so it propagates between Z and W, but there's this influence of Z star in this delta function. Okay, so those are the propagators. And then there are a bunch of vertices. Because of the axial gauge, actually the Chern-Simons 3 vertex cancels out. You don't get any contributions from the A cubed term. But you do get all those contributions from the non-local integral over log det term. And so these take diagrammatically the form of sort of arbitrarily many insertions on some fixed line x that then needs to get integrated over. So the pictures are made up of these objects. And when you start computing, this is the kind of objects, diagrams that you start writing down. Again, this is all following Mason and Skinner's formulation. So they write down diagrams like this, where you exchange a propagator between two edges of your loop in momentum twistor space. The end result of this is this basic superconformal invariant object made of 5, totally antisymmetric object made of 5 momentum super twisters. It's a 5-index object. One of them is the axial gauge reference super twister, and then between these edges I have I-1I, J-1J for the two edges. Okay, and that's a Grassmann degree 4. This is like the NMHV tree level computation for scattering amplitude. In amplitude language, it's called NMHV tree. Okay, so that's the first object that you get with a simple propagator. So that's the supersymmetrization, as well as MHV, which would have been corresponding to the ordinary bosonic Wilson loop with just gluons drawn in the picture. We've now acquired this stuff that also has the Grassmann degrees of freedom, thanks to this Mason-Skinner super twistor formulation. And you can compute NMHV amplitudes using that. But you can also compute MHV amplitudes. So you can go back and you can compute, for example, the diagram that inserts one of these lines, x, that needs to be integrated over. And then you get a contribution of a propagator going from an edge to the line and from the line to another edge. And this is given by the so-called Kermit diagram, which just gives you some formal integral to do. We won't worry about doing this d for x, a, b yet. Integral over the line. But I get some rational function that needs to be integrated that depends on the line. And it has some schematic diagrammatic representation that's these wiggly lines are somehow meant to represent this numerator. And then there's these triangles with these 6 propagator objects in the denominator, 4 of which are spurious because they involve this momentum, this reference twister, only 2 of which are physical. Sitting here. And for some reason, somebody thinks this looks like Kermit. So this is called Kermit. All right. So that's how you get MHV. So it looks rather different in this formulation. Unsurprisingly, because we're computing in this Chern-Simons version of the theory rather than the original space-time version of the theory. However, you can show that you get the same answer back. So if you sum over all diagrams for the NMHV, tree-level NMHV contribution, you just get the sum over all these diagrams, and after doing the sum, star drops out. Okay, this we know, this is like the MHV rules version, I guess, of the NMHV tree-level computation. If you do the Kermits, you add up all the Kermits, and then already at the level of the integrand, you can sum over, if you add up all the Kermits, you see star drops out. And in fact, you can rewrite it as a sum over chiral pentagon integrals that schematically look like this, and I didn't write what the integrand is, so this is maybe not so helpful, but if you know this picture, this is what it is. It has some dependence on some auxiliary point x, or auxiliary line in twistor space, x. But this side didn't depend on x, and this side didn't depend on star, so both sides are independent of both. Okay, and if you add up all of these objects, you indeed see x cancels, and you get that same function that I computed for you before by sending a gluon across between the 2 loops in the space-time version of the picture. Okay, so this should reassure you that this funny-looking version of the theory does indeed compute the same thing that we computed in the ordinary space-time version of the theory, with ordinary bosonic Wilson loops, and I get the right answer in the right place for this MHV object. Okay. Right, now, what I showed you before was again a contribution to the abelian theory for the same reason that there's a color structure that's the same. So if you want to go to the SUN theory, you have to go to the next order to get something that's not vanishing because of the same color reasons. But again, you get something that's essentially the perfect square. So you can sum up the 2 abelian-looking diagrams, take the total square, and that's equal to the diagrams that you would compute at that order, where you send 2 propagators across. That would give you an n squared MHV tree. 1 propagator across and 1 via a line, which will give you n MHV 1 loop. And then 2 propagators across, both via an intermediate line, which would give you NHV 2 loops. And now I'm using this very schematically simply to count the Grassmann degree. Okay, here we're not dual to an amplitude, I'm just using the same terminology to compute the degree in Grassmann variables where we're sitting. Okay, so you can write it out. This is the answer. Perfect square of these objects. Okay, let me skip the statements about the abelian theory and skip statements about the Q-bar equation. I could come back to that if there's interest, but I wanted to tell you about BCFW. Probably out of time. So this is a rapid version of the BCFW. The schematic idea is follow these guys, and you do this holomorphic linking procedure. And so what you do in BCFW is you introduce a parameter, and you deform your curve according to this parameter. You get a family of curves that now depend on a parameter, t. To get BCFW in the standard form, what you would do is simply slide Zn along its line towards Zn minus 1. with some amount t. Okay. The end result of this is that you can compute this variation of the expectation value of the loop, and it comes out in terms of a correlation function of two loops. And the two loops are given by... so what happens when you slide the line around? So imagine I take this line here, and I'm moving it around to all places where I could draw this dashed line. Now, if I slide a line around in P3, it will intersect every other line in P3 at some point. Right? At some point where I change my parameter, it will intersect all the other lines in the geometry. So at some point it will intersect, it already intersects this line, but at some point it will intersect this line, this line, this line, this line, and so on. And you get a sum over configurations that are somehow special. Okay, so, right. So this is meant to be the picture that's associated. So I slide Zn along this edge, some special point Zn hat, such that this line, which was 1n, intersects some other line, j minus 1j. And then I get some special intersection point I, where the two things intersect. And then the variation is meant to be an integration, but it gets localized to these points where these intersections happen, and you get a sum over these contributions that come from these special intersecting topologies. Right, so I thought I would, maybe I'll give you, just try and sort of flesh that out slightly. So, to give you a hint, but really what I'm going to be doing is I'm just following what's in this Bullimore-Skinner approach to holomorphic linking, and then at the very end I'm going to generalize to our new object with multiple loops. Okay, so this is just a reminder that we've got this holomorphic Chern-Simons theory. We'll ignore the log det term for now, because that's going to give us these loop collections. So we'll just do tree level. So we're just working in holomorphic Chern-Simons theory, and we've got our loop operator that I introduced before, which is this sequence of parallel transports around the contour. Okay, so what do? You introduce a family of curves, as I said, parameterized by t. Ultimately, it will be that one in the picture. And then what you do is you compute the variation with respect to that parameter that you've introduced, and you can show that if you compute the variation of the loop operator, in fact what happens is that you insert the curvature tensor, gauge field strength tensor, into the trace of the Wilson loop at some point z. Okay, and then you have to integrate that around the loop, and you pick up. So you basically have to integrate this curvature inserted against the holonomy that you already had. So this is now inside the gauge trace. Okay, and you can write that using your holomorphic Chern-Simons action. If you compute the variation of the expectation value of this loop operator, that's formally given by a path integral where you integrate over all these connections. And you can insert this variation of the loop operator into the path integral, and then you can reproduce the insertion of this field strength by taking a variation of the action with respect to the connection. Okay, so that's just reproducing this insertion here. And then what you do is you integrate by parts inside the path integral to get this variation of the gauge field to act on the holonomy. So that reproduces something like this. So you have to take a variation of the gauge field acting on this concatenated set of parallel propagators. Okay. Okay, now you can show that if you take one of these components and you take the variation with respect to that component, So this thing, of course, I'm writing out the matrix indices now, right? Some fundamental UN or SUN representation object that carries some matrix indices. And then you can show that this thing actually you can write as an integral over these parallel propagators to some point, some intermediate point z prime, where z prime actually gets identified with a delta function with the z that you were taking the derivative at the point you were taking the derivative with respect to the gauge field. Okay, so this is actually the term that Bullimore and Skinner write down because they do the computation in UN. We actually need this term also because we need to do our computation in SUN. Well, we're interested in doing our computation in SUN. So there's an identical term, but just with a different gauge structure on the index structure. There's a diagonal term here that I need to subtract out. Okay. Right, so now if you insert that into the variation of this expectation value of your loop, then you get the thing that was advertised before. You get this thing that this delta function forces you onto points where z and z prime, two components on the loop, actually have to agree with each other. So it's actually forcing the loop to self-intersect at some point. Okay. And then what you get at that point is the correlation function of two different loop operators, each of which comes from a piece of the original loop, like the left half and the right half in this picture. So I get a loop operator that just goes around these points up to the intersection point, and another one with the same intersection point that goes around the other points. Okay, and then in SUN there's a corresponding term where I do nothing and I get the original loop operator. Okay. Then what they do is they take the large n limit, and in which case this SUN term vanishes because it was suppressed in anyway. And moreover, as we all discussed before, the expectation value of the two operators factorizes. Right? The leading large n contribution to the correlator of two loop operators is actually the product of the two individual loop operators. And that's the same here as it was down there. Right? That's just a statement about the color structure, which is just this some SUN that we've got going on. So you take large n, this thing factorizes, this thing drops out, and we're left with a formula that looks as advertised. We get this product of a left Wilson loop and a right Wilson loop on that contour where the thing is, the left and right are defined by this intersection point. Okay, so there's the picture. And then, then you can choose a variation, which is the one I showed before, where you slide Zn along the line from 1 to n minus 1. You slide Zn along the line from Zn to Zn minus 1 with some parameter t. And that moves the line 1n. And then that's the line that ends up intersecting j minus 1j in this picture. And then, then you can show, given that the variation, you can compute what's the difference once you do this slide, and you find that the answer for your original Wilson loop, where there was no deformation, is the answer where it went all the way to the end, where there's just one fewer point, and one of the lines drops out from the computation, plus these contributions from all the intersection points, with one of these basic superconformal invariants with indices n minus 1, n1, j minus 1j, so it's defined by the intersection point, and then Wilson loop left and right. Okay, this is exactly the structure of the BCFW recursion relation, right? This is on the amplitude, it's like the n minus 1 point amplitude plus the sum over left and right factoring on the residues for the z deformation. So that's the BCFW recursion relation written in momentum twister language. Okay, and then some special points in the geometry. There's obviously this intersection point given by this, and there's the special point where the lines intersect, where this Zn hat has got to, that's given by this. Okay, so that's how you recover BCFW using this holomorphic linking pictures, literally following Bullimore and Skinner. And now we generalize, we just use the same approach, and we ask what happens if we want to compute a correlation function of multiple loop operators, for example, 2 of them. And with this I'm nearly done. Okay, so this is the end result. We pick a deformation, and we just pick one of the loops and slide one of the points along one of the edges on that loop. And then that line will start intersecting other lines in the geometry, all the other lines on its same loop, and all the other lines on the other loop at some point. Okay, so that's what's happening here in this picture. You get 2 different kinds of terms. Okay, so this structure is the same. The thing you want is the thing with 1 point removed plus all of the intersection point contributions. You get intersection point contributions. So the thing we want, we want to compute the connected part. We know what the product part is already by BCFW. So we're interested in this connected part of the 2 loops. So what do you get? You get, again, this basic superconformal invariant of the same structure, n-1, n1, j-1j for the line that it intersects. And then you get terms where it intersects stuff from the same loop. So these are these terms. You get terms here which basically factor one of the loops. Factor, so we have to be slightly careful. So you get what you actually recover is now still the connected part of these 2 pieces. So you get the connected part of this half of the loop with that guy, the spectator, times this part of the loop. So that's the factorization. And then likewise I get this part of the loop times the connected part of this half of the loop with the spectator. That's diagrams that come about when the line intersects one of the lines in the same loop. So that's sort of analogous to what we already saw. And then there's a new type of term where the line goes across and it intersects a line on the other loop, and you get an invariant that has n-1, n1 on the first loop, but then it has j-1j on the other loop. Okay, and that comes with something interesting. So you get now a new type of term, which is where, so this is the picture, you've got the intersection point now joins the 2 loops up. And now the gauge trace, instead of following 2 contours, what it wants to do is it wants to go around the big contour. So you go all the way around, and then all the way around this way, and back to where you start. So what you actually compute is not a correlation function of loops, it's one big loop that goes around in the color structure, it goes all the way around both components in UN. And then there's a piece where I have to subtract off a diagonal term in SUN. It would look like this. Okay, so that's the new feature of this recursion relation. It takes 2 pieces, 2 contours, and it glues them together into one big one. Okay. All right. So now some sanity checks for SUN. I told you. Let's see if we can get this to work now. So I told you that NMHV was 0, right? Because for color reasons, there's no NMHV amplitude for the connected part. Okay. So if that's true, this should say connected. So if that's true, 0 should be 0 plus 0 plus 0 plus, and now I've got something that's NMHV here. This is Grassmann degree 4, this basic superconformal invariant. So I need this to be 0, but this is 1 because it's Grassmann degree 0, so it's MHV at tree level. It just gives me a factor 1. And so, in fact, it is exactly 0 for SUN precisely because of the terms that we now didn't drop. I have to have 1 minus 1 times 1 to get my 0. And I have to be careful to keep track of the SUN nature of the object. And if it's not SUN, I don't get 0. But that makes sense also, because we saw that's really, yes, the connected part. Right, so sanity check number 1 works. Sanity check number 2, the n squared MHV, or Grassmann degree 8 object, is meant to be a perfect square. It's meant to be the sum over all star I minus 1 I, j minus 1 bar, j bar minus 1 j bar, right, I and j on the 2 different loops, all squared. Because I told you the thing factorized when I send 2 propagators across. So this has to be the answer. And it does work, but it's not at all obvious from the equation. You have to work quite hard to convince yourself that this equation does in fact predict you this answer for n squared MHV, but it does. Okay. All right, so I'm sorry I'm overrun, so let me just finish up. Right. So, again, I was meant to comment, but let me say what I've done. So, we followed this formulation of Mason-Skinner, and we used it to compute some Wilson loop correlators, multiple loop objects, using this supersymmetric formulation. We got some basic simple structural answers about the simplest components. We didn't verify a generalization of the Q-bar equation because I skipped it. But we did obtain a generalization of the BCFW recursion relation using this holomorphic linking approach. And we verified that we were getting sensible answers out of it. Although the second verification requires some somewhat non-trivial computation to check that you get the same answer. Okay, and I did everything at tree level, so it's like the generalization of the tree level BCFW recursion relation for a single loop. But you can include that other term in the action, which I just dropped while we were doing BCFW. And if you include it, what you get is the BCFW recursion for the loop integrand, both for a single loop, which reproduces the all-loop BCFW recursion of these authors. And you can get that similarly through this holomorphic linking approach using the log-det term in the action as well. If you put that in, that's very straightforward and it's very similar. You get the integrand recursion relation also for multiple loop objects. I just didn't do that computation. Okay, and then the final comment was meant to be that there should be something interesting. Now, I do not know what the underlying geometry should be, but since we've obtained the generalization of the BCFW recursion relation, and what it does is it takes, so the original one took disk-shaped objects, and it glued other disk-shaped objects together to get a bigger disk-shaped object. Right? That was BCFW. So very cartoon now. This is definitely a cartoon. BCFW is basically saying something like this, where you glue stuff together with some operation, right, and you make a bigger disk. So this object is something more like an annulus, right, because it has 2 boundaries, if you have 2 Wilson loops. And then what you get is, okay, so you get a boundary term, and then you get a sum over terms that look like this, where you glue another disk on. That was 1 boundary. You also get terms that look like this, where you glue a disk on the other boundary, okay, and you obtain 2 annulus terms like this. And then the new term is terms that look like this, where you take a disk and you bend it over on itself, and you glue it together at some point to do with the intersection point, and you obtain a new contribution to the annulus shape. Okay, so this was the sort of the novel term. So, it looks like there's some natural association of genus to this picture, there clearly is, that's related to the topology of the points. It would be very interesting if that could be related to a generalization of the Amplituhedron, which sort of admits this higher genus picture. But it will be interesting to talk to experts on the Amplituhedron to see if we can understand what's happening. So I'll finish there. Thank you. I'm sorry for overlapping.
Thank you for the very interesting talk. Are there some questions?
So these exchanges between different Wilson loops, the diagrams are finite, right? Because all the divergences just come from the corner.
So at leading order, all the diagrams are finite. The ones that I showed you, they're finite. But if you go to the next order, I can have stuff going across and stuff that's near a corner.
But can you somehow define another object which would subtract these divergences?
Oh, yes. Absolutely. Yeah, right. So, okay, absolutely. So I did, but maybe it was sort of a bit opaque. Let me go back to what I said here. Finite parts. Okay, so this was the general structure, right? So we agree on this. Yeah? So, okay, so then the claim is that the divergent structure looks like this for the multiple loops. It's just a product over everything that you've got here for each loop individually. And then there's some new interesting finite piece. So if you prefer, instead of me defining the finite piece this way, you could define... that was lucky. Ran out of battery. So we could define we could define it by the correlator divided by the product of the individual factors. That would be finite. I'd cancel all the divergences and the anomaly, and this would be like a ratio function type definition for this object, if you like.
So choices on what to put on the denominator, like the...
So the natural choice actually, I think, is actually not this one, because it's the one that I wrote down for you before that I defined as R, where I strip off only the divergences and anomalous conformal piece for each of these pieces. And the reason for that is the thing I didn't show you, which is that that's the object that naturally satisfies this Q-bar equation. And then but obviously they're very simply related to each other, right? It's just the only difference is the remainder factor for each of these individual pieces down here.
Just wondering if you're seeing any hint of cluster adjacency in this picture?
Don't know yet. So why do we not know? Because, although it's a very interesting object, it's slightly hard to compute these things. I gave you an example of this perfect square piece, so one could look at that piece. Now that thing is a square, so adjacency doesn't like things being multiplied together, right? Because for the shuffle reason. But that's a very particular thing that gets multiplied together. And so it might be that there's some, as is the case for the Wilson loop, single Wilson loop actually, you have to make a very careful definition of your finite factor in order to reveal adjacency. If you make the wrong definition of the solution of the anomalous conformal part, you will pick up pieces that multiply through and sort of spoil adjacency. It's only with the right definition for the anomalous conformal piece that you see adjacency, and it's actually not the one I wrote down here. You actually have to adjust it, even in the case of the single Wilson loop. Moreover, actually, you can only do that in cases where n is not 0 mod 4. So there's already a problem for spotting the full structure of adjacency at 8 points for a single Wilson loop. Now I'm talking in terms of polylogs, because that's sort of where adjacency arose. But of course you could also study the singularities of BCFW terms. And then you get a kind of abelianized version of adjacency, where every pole factor is next to every other pole factor. So I don't know the answer, because it's not quite clear what the right positive structure to look at is. So it's true, and it's still true, that if I take two squares, right, I've got 8 points. So this does live in GR4 of 8. It clearly doesn't want to naturally be associated with the canonical positive part of GR48 because it's got a different cyclic structure associated to the data. And therefore, because I struggle with understanding the cluster structures associated to other bits of these spaces, I don't know what quite to look for in order to see how the poles want to talk to each other. Maybe the amplituhedron, if it does generalize, might give a clue as to what you should look for. I don't know. But, so, it's, definitely interesting to try and understand.
So the poles might not be cluster variables, but the permutations of them. So
right, there's no reason to expect this data to want to naturally be associated to the cluster structure on 8 consecutive ordered points. But that doesn't mean it doesn't have one, it's just another cluster structure associated to some other regions in GR48. Maybe multiple cluster structures, I don't know.
At the tree level, do you understand the structure of singularities for this? You calculated some of the answers already. So do you understand where the divergences are?
What holes you mean? What holes does it have?
So if you want to find geometry, then probably you want to know where the boundaries of the street.
Yeah. So all right, absolutely. So you could look at this, right? No, you can't. So let's be abelian again. You could look at this object just as a starter and ask where are its singularities. So the physical poles are all of the form I minus 1I, J minus 1, J bar minus 1, J bar. Right? Bar means you're on the other loop. Physical poles are... physical poles are of that form.
It's for every MHV level, or
this is NMHV only.
okay.
Yeah. So and I'm being abelian. So the real answer, the first interesting answer, is really the square of this, right, in SUN. And you might worry there it's going to have double poles, but it doesn't because of grasping reasons. So it does only still have simple poles. But okay, so either this or the square of this. And these are the singularities. And then you could wonder what are the correct positivity conditions that might only have these as boundaries, right? That's what the kind of starting motivation is. And I think I did at least work this out, but I don't know how much faith to put in it. So what is it? So we want this positive, and we want... It's not everything positive. We don't need that, right? We need... Okay, from my memory, if I'm remembering it's IJKL on one loop, and the pair... IJ K bar L bar, and I bar, J bar, K bar, L bar. Positive, I think. Sorry, I've forgotten now. Maybe we can. It's very simple to sit down and work out what it should be in order to have only those poles as boundaries. So maybe this gives a starting clue as to what kind of geometry that you would like to. But remember, this is also slightly hazy because this is not really the answer. This is the abelian version. And then the full answer is the square of that, which I guess you could say has only the same pole, so maybe that's okay to start with. But then then things become quite complicated, and we can do computations, right? We do have an n-cubed tree-level answer that we've been playing around with and studying. We needed it for the Q-bar equation, in fact. But it's quite a cumbersome object, let's say. And we compute it with the reference twistor formulation, and I think we have verified also the BCFW version. But it might require some patience to disentangle exactly what the singularities are.
And can you think about the correlator of two of these loops as in some limit as a single loop. For example, if I take two of the points to be like separated, for example, I could imagine I could extend it by some lines which connect them, right?
Oh.
And
So
so that configuration is, it's not generic configuration, but that configuration will be like a limit of a single operator.
right. Let's see. So there are various limits that are suggested. I'm not sure I've studied that one, so I don't know the answer. But you could, I mean, you're trying to say something like, if I draw it in space-time, right, you want an edge that, sort of, I don't know, I'll draw it like this, and then this continues somewhere, and you want me to put an edge of the other loop on this line, right?
For example, yes.
Yeah.
So if you're in dual space,
Yeah, so then you might expect that this would somehow be related to
exactly.
something that...
Yeah, and this looks like a single object.
Yeah. Yes, it's not. It's actually slightly non-obvious because of the divergent structure. So you have to worry about what's happening at these corners. You think just sort of, like by backtracking, this would cancel out, and so I can freely add this. But since it's a divergent object, that may not be the case. So yeah, I'm not sure. I haven't really studied that limit. It's interesting.
Can you relate this to local correlators by taking
I think so.
two like cyclic limits?
Ah, I know what yes, probably, yes. It would be really interesting. In fact, that was one of the avenues to try and study and understand is, could you start from the correlahedron and do a multiple sequence like limit and understand the whatever amplituhedron geometry should be from that structure? Yes, absolutely. In fact, I wanted to talk to you about exactly that. Yeah. Yeah.
There's also lots of data there, right?
Right. Yeah.
To how many loops now? 14 or something?
Right. So integrands should be available. Yeah. Right. That's I can't remember how many points that you look at and so on in that. But yeah, it would be really interesting to discuss.
Are there more questions? If not, maybe let's send James again.